Okay. Now, so I think we are, let me see how many of you are attending today. Okay, 12, so I think we are fine. Thank you. I have 3 minutes delay because I got a new board, a graphic blackboard. So I was trying to, yesterday to set it up and today to learn how to use it. I hope it will run fine, but you will be my guinea pigs today. So I hope you don't mind, but I think it is nice. And today, first of all, I wanted to discuss with you our plan. This is our 5th week, if I'm not wrong. We still have 3 weeks left. We are quite on schedule. And I think there is no need to rush. I just wanted to let you know that I had another booking for a presentation too, actually. Emiliana after Easter and Anna for next Monday. So I think Anna, this is fine. Next Monday you can present, and I think you should take as usual. You should plan for taking like 8 minutes, 8-10 minutes, not more than that. And you already have seen, all of you, the style of the previous presentations. They were perfect. Different styles actually, because the first one was on a global perspective. The second one was more on let's say regional problems, not local, regional problems, regional water resources management challenges. So 2 different styles, but I think the way of presenting it, everything is perfect. So I think you can emulate these styles or feel free to be creative. We are here to also to make experiments like I am doing today with the graphic board. And you know, this year we are doing a continuous set of experiments. I think it is nice because it's an opportunity, you know. I think I already told you, we experienced some changes in the past month. And in a normal situation, these changes would take like 5 years to occur. Like moving to online teaching would take like 5 years. And it happened in 1 month. So, I mean, it is not a positive situation, but on the other hand, there are, as I said many times, opportunities. Okay, good. So Anna, be prepared. At the beginning of the lecture, you will have your 10 minutes and then the discussion afterwards. Okay, I think I can start by sharing my graphic blackboard. Let's see if I can succeed. Yeah, here it is. You should see it. I'm checking on the phone. Yeah, everything is fine. I also think today I shouldn't have any connection problem because I had a problem actually in my router, which I think I solved. Let's hope so. Okay, and then let me see, everything is working here. This is the page of our course, and we are at model calibration and validation. So I just want to go back here because we already discussed model calibration, but I want to discuss now model validation, which is a different story. And so there is, let me pass to the other view, which is more, it is large. No, this is the same view. Just 1 second. I think it is here. Yeah, it is this one. 1 second. Here it is. Okay, good. So, as I said, we talked about calibration. Now let's talk about validation, which is here. So what is validation? Validation, it's a way to check model performances. Calibration is a way to optimize the model performances. Validation is a way to check them. Because calibration, it is of course a very nice process, a very nice way of making the model able to simulate what we observed. On the other hand, calibration has a downside. The downside is that it's a kind of model training, and you train the model against the situation that you used in calibration. So in calibration, you have a given hydrograph, and you train the model to reproduce that hydrograph. But actually, what you want to simulate, what you want to use the model for, is not the observed situation. You want to use the model for simulating something that you don't know, something that you didn't observe. What you observed is already known, and making the model able to reproduce what is already known is not our target. Our target is to make the model able to reproduce something that we don't know. So is the model, this is a challenging question, is the model able, after calibration, to reproduce what we called an out of sample situation, out of calibration sample situation? So is the model able, again, to reproduce an out of sample situation? This is a challenging question. And of course, we have to find the way to check whether indeed the model is able to do that. And again, what we want to do is to use data. We could also use expert knowledge. We could gain an expectation of what is going to be the system in a future situation, the situation we want to use the model for. But of course, if we have data, this would be a better solution. But do we have data? Yes, we have data because we calibrated the model. So given that we assume that the model was calibrated against data, we have the data. On the other hand, we used that data for calibration. So the idea is to make an experiment, and the experiment is called validation. And precisely, the idea could be, for instance, a very simple one. Let's calibrate the model only on half of the data and use the other half to check, to perform an out of sample simulation. So this is a very simple and trivial idea if you want. And let me go just 1 second. Let me make an example. What you see here is an hydrograph. This is my graphic board. You see, it's very nice. So, and what you see here is an hydrograph, and you could use this hydrograph taken from Wikipedia to calibrate your model. But another possibility is to split the hydrograph into parts. Okay. For instance, you can split here, and I take this, and then you could use this part here to calibration. So you have to forgive my writing, I have to learn. This could be calibration. So this could be the set of data that you use in calibration. And then you could use this second set of data for validation. Which means that you estimate the parameters here. Here you estimate the parameters. You get the parameters from here. And then in the second part, you check the parameters. Check parameters. Okay? This is the idea. This is called precisely, in technical terms, it's called split sample validation. This is the split sample validation. There are some questions here. The first question is, if I use only half of the data to calibrate, then my model is, the parameters are not calibrated by using the full set of data. So I get an higher uncertainty in the parameters. You may remember that I said that uncertainty in parameters goes down, decreases, for increasing sample size. You remember the sample size. The sample is our data set. So the sample is the data set, and the sample size is the number of data. Okay. So for increasing sample size, we have uncertainty which is decreasing in the parameters. And therefore, if I use for calibration a reduced set of parameters, my uncertainty in the parameter increases. This is true. And then, but we can accept it. We can accept it for the sake of validation. So what we can do is, let's start with half of the data to calibrate the parameters. This is also something that it's nice because you know, calibration takes longer if you increase the sample size of the calibration data. So if you reduce the sample size because you split the data, then it's also nice. And then you get a parameter set. Let's assume that this is not the final one, it's temporary. It's just for the sake of validation. And then we use this parameter set to perform a validation, second half of the data. If we are happy with the validation, this means that that's okay. And then we can finally recalibrate the parameters by using the whole data set. And you may say, okay, but in this way, the final parameters values are not those which I validated. But this actually is not a big problem because, I mean, you can accept, this is a second order uncertainty, you can accept it, and also you can use your expert knowledge to make a check of the reliability of the final parameter estimate. If the final parameter estimate is not much different from the transitional parameter set, the one that you calibrated by using only half of the data, you are happy. If you see that the final parameter set is much different, then you know you may be in doubt, and then you could perform a different validation. You could use a different technique for validation. But actually, this is the rationale. The rationale is to save some data to be used for validation. And I said half of the data, but you could decide that it's more than half, less than half. It depends on your situation, on your expert evaluation of the model and your case study. And also, as I mentioned, there are more refined ways to validate. For instance, another idea could be if you decided to use the split sample, and if you decided to split the data in two parts of equal sample size, then you may have the idea of performing two validations. And two validations because you could use in a first validation the first half of the data to calibrate and the second half to validate. And then you perform a second validation. You use the second half of the data to calibrate, you exchange them, and the first half to validate. And you may also check whether the parameter values remain more or less the same. If they remain, again, more or less the same, you are happy because it means that your estimate is stable. If they are fluctuating a lot, then you may be not very happy, okay? And you could extend this idea. For instance, you could split the data in two parts of not equal size. Like you could decide to use 10% of the data for validation, 90% of the data for calibration. And the 10% that you use for validation could be the initial 10%, the second 10% from 10 to 20, the third, the fourth, the fifth, and then you get 10 validations, 10 calibrations and 10 validations. And this is also called Jackknife cross-validation. So against the split sample, which assumes basically that you split the sample only in two parts, the Jackknife cross-validation, or Jackknife validation in short, the idea is that the data are split in more than two parts, or let's say they are split in a way that you are allowed to perform more than two validations, because you move the validation sample along the whole set of your observed data. I'm not going into the details. I just wanted to, this is in a way a question that I may ask at exam, and you have also the description here. If we go to the web page, and I think there is a link here. You see in the bottom. Let me select it. There is a link which is to a Wikipedia page. And if you open it, you know, this is cross-validation. It's not called Jackknife here, or maybe that there is somewhere. Let me check if there is somewhere the term. Not necessarily is there. Yeah. Or actually, they make a difference here between cross-validation and Jackknife because it's actually they use a terminology here which is which refers they use the term Jackknife for parameter estimation, not for validation. So, you know, the terminology in different disciplines is somehow different. What we mean in hydrology with the Jackknife, usually it's the validation, not really the parameter estimation. Even if, you know, they are very similar, because each time that you validate, at each step, you also calibrate. So it's not very different, but you know, the terminology and the terminology is a little bit different in different disciplines. But anyway, here you have an example of, you see here, for instance, it says one round of cross-validation involves partitioning, I am selecting, a sample of data into complementary subset, performing the analysis on one subset, called it training set, and validating the analysis on the other subset, called the validation set or testing set. To reduce variability, in most methods, multiple rounds of cross-validation are performed using different partitions, and the validation results are combined, for instance, they may be averaged, over the rounds to give an estimate of the model's predictive performance. This is precisely what I meant to say. So what I also was saying at the exam, I can ask you what is split sample and what is cross validation. So just keep in mind cross validation, which in hydrology is often called also Jackknife. Keep in mind what is the meaning, and then I'm not giving any more details. Okay, so I think, let me go back to my web page. Yes, I think we are done for calibration and validation. There is another link here, and let's see what is it. This is actually a link to a paper that I am a co-author of. It's not necessarily that you read it. It's just an example. I think it is available. It's available, not really available because it's copyrighted, but in any case, you can request the full test. But it's not necessary that you read it. We tried to formulate here a code of practice because, as you see, I just mentioned two ways of validating models for water resources assessment, but actually there are other techniques that could be used. And also the question is how to finally present the results, how to finally derive an indication of model reliability. As I said, a solution could be averaging the performances, but there are other solutions used in hydrology, and we called here for a unified way of presenting model performances. So this is just to describe what is the essence of this contribution. Very good. I think, as I said, that for this lecture we are done. Do you have any question while I'm moving to the next one? I assume that in my lecture that you are familiar with terms like sample size, what is a sample, what is an observed sample, what is a validation sample, etc. Try just to get familiar with the terminology, because it gives to you a way to better interact with your customers, your clients, your stakeholders, etc. Okay, I think we can go back to the page of our course, which is here, and then we can go to the next lecture. It's design of river barrages. this is a technical part. I told you at the beginning of this course that I want to focus on technical design, at least for part of the course, and this is one of these focuses, technical focuses. This is the most technical, I would say, and I wanted to propose this lecture because I want to give you an idea of what the technical design is. We will not go into the structural details of river barrages because structural engineering is done in other courses. I just want to focus on hydraulic design of a very simple infrastructure. It's very simple, but actually it is just because it's simple. The river barrage is basically simple, especially if it is a small one, as we will see. And just because it's simple, I was saying, it may happen to you that you are asked to make such kind of design at the beginning of your profession. Actually, this is what happened to me. Just after I took my master's degree, I was asked by a professional engineer to collaborate to design a river barrage. There is not an extensive literature, so it was not an easy task at the beginning of my profession, and I think it is a nice example. Also, the river barrages, the small ones, are an infrastructure that is more and more frequently designed today, and the reason is that today there is an increasing interest for small-scale hydropower plants, small hydropower plants. They are also called mini hydro plants. And the reason why there is an interest is that, you know, we have an increasing demand for energy today, and we have an increasing demand for energy, and I would say an increasing concern about environmental impact of hydropower plants. Hydropower plants have the nice feature that they produce renewable energy, and therefore they contribute to minimizing the CO2 emissions. They contribute to the mitigation of climate change. On the other hand, they may have a significant environmental impact in terms of impact of the infrastructures. At the beginning, they were massive infrastructures. They were dams, basically. So it's a huge impact for the infrastructure itself. There might be an impact in terms of risk of failure of something, which may determine risk for humans, for human society. There is also sizable environmental impact related to the modification of the river flow regime and the interruption of the ecologic chain in the river, because barrages are barriers, and when you build a barrier on a river, of course you make an impact on the ecology of the river. You make an impact on the fishes, on the animals, and microorganisms. So there is indeed a significant environmental impact also on groundwater dynamics, which you may easily understand. And of course, the greater the infrastructure, the greater the impact. And therefore, you know, today there is quite a significant debate on, okay, renewable energy is fine, but on the other hand, we have to find a way to produce renewable energy by minimizing the environmental impact. And this reasoning applies also to wind power, applies to solar power, different impacts. For wind power is visual impact and noise. For solar power is visual impact, which is very significant because of the extension of solar plants. And as I said, for hydropower, it's a question of visual impact mixed with a broader environmental impact on water resources and the groundwater dynamics and the river ecology, etc. So it is a very significant discussion, and given that the larger the infrastructure, the larger the impact, of course, there is an increasing interest for small-scale infrastructures, for mini plants. And also we have the technology today that allows us to efficiently use mini plants, efficiently use only very small portions of the riverbed. Actually, the dam has an impact on a large portion of the riverbed, the small-scale plant usually gives back the water just downstream, and therefore the impact is limited. It's not actually it's not absent. It's limited. Still, getting the permission to build these plants, it's not easy because of the bureaucracy related to environmental impact assessment. It is nice that we are concerned by the environmental impact. On the other hand, we don't have to exaggerate because we have to find solutions, alternatives to burning fossil fuels, and therefore, you know, at a certain point, we have to take decisions. And the contribution of the engineer, once again, it's very important in that, because the engineer is expected to be unbiased, is expected to be prepared, even if, you know, it's challenging because we need to be prepared on several different disciplines. I already made this point. And the engineer should provide a transparent view which is not affected by political influence, which is, I mean, it's not negative, the political influence, but it's just something that may lead to the development of a biased view, something that needs to be further discussed in order to compare different views. The engineer is supposed to provide an assistance to these discussion by presenting the reality, by presenting pros and cons with an objective view. Yes, it's challenging, but still. And so the reason is, the moral of the story is that there is an increasing demand for designing small river barrages. So let's go to this page, then, design of river barrages. And first of all, let's, as usual, categorize them. I am a fan of categories because it helps you to remember. So let's say that river barrages, we could classify them by distinguish between what we call dams and what we called actually river barrages. And so these are retention structures retaining water. And so about the dams, we can distinguish between concrete or stone masonry dams, okay, earth dams. We don't discuss dams in detail, but it is just, I just want that you know that there are two main type of dams. Let me try to select both of them. Yeah, concrete or stone masonry and earth dams. Usually the second solution is preferred when you have a soil, a geology that requires flexible structure. Let me use this word, which is understandable even if not very technical. A plastic structure. This is a bit more technical. So if you have a setting, a geological setting that is adjusting, slightly moving, then an earth dam is more plastic and can adapt to small movements, to small adjustments of the foundation, etc. Of course, earth dams cannot be very high, but we have examples of earth dams that are quite significant height. They can get to even 100 meters. Of course, their extension in the longitudinal direction of the river is higher than the extension of a concrete or stone masonry dam. You can find on the web several examples, several pictures for both of them. But as I said, we are not interested in dams. There are also other types of dams, other material besides concrete and earth, yes. There in the past also wood dams were used. Now they are less used. Wood is used for building barrages nowadays in some cases, but not dams anymore. It may be possible, but usually they are not used. And then we have the river barrages. What is the difference between a dam and a river barrage? The difference is very simple. It's the amount of water that is retained upstream. A dam retains much more water than a river barrage. The river barrage, in principle, is built like a dam. There is no much difference. In principle, it's a transversal structure, transversal with respect to the river direction, which aims to retain a little bit of water upstream or much water upstream. If it is much water, we say it's a dam. If it's a little bit, we say it's a river barrage. And both of them have also the task, the role of keeping the water level upstream fairly constant, or let's say not much varying. And this is because if we want to get water from there, the lower the excursion of the level, the lower the variability, and the finer and the more efficient our water withdrawal is. So I said that the difference between dams and barrages is much water or a little bit. Let's be more precise, because we are engineers, we cannot say much and a little bit, or we can use these terms, but at the end of the story we have to be technical. And in Italy, the law in force makes the difference based on two conditions, which is the height of the barrage and the volume of water, the max volume of water that can be retained upstream. So here you can see that I am selecting. In Italy, dams are defined as structures that are either more than 15 meters high, or originating in upstream storage of more than 1 million cubic meters. How are these measured? So the height is measured from the foot of the foundation to uppermost part of the structure that can be surmounted by water. Okay? How is storage measured? Storage is measured at the highest regulation level. 1 second, I take a note, because I want to check one thing here. I tell you, I want to check what I want to check, because there was a change in the Italian law and a change in the measurement of the height. And the change is that the height can be measured with respect to the foot of the foundation or the undisturbed river level before building the dam. And I think this is correct, but I always don't remember which is the now that is currently in force, because in the new law they changed it. So it was, I think the correct one is measuring from the foot of the foundations, but I want to check, because it's every year I have this in mind, because they changed it recently and I never remember what was the old version and what is the new one. So just I want to be very clear, because I think that you may also learn from the doubts that I have, and let me put it in an elegant way, and I'll tell you. And okay, and then instead I am sure of the measuring of the storage. Storage is measured again. Let's learn this, because this is something that I may ask. Storage is measured at the highest regulation level. Okay, so if you get either the first condition or the second, it's just sufficient that you have one of the two conditions that is met to classify it as a dam. So if you pass 15 meters or the storage is more than 1 million, then it's a dam. This is extremely important, because dams are subjected to national surveillance. And there is a body, a governmental body, which is managed by the Minister of Infrastructures, that is in charge of surveilling, monitoring the dams. And there are a series of procedures that they have to complete at a regular time step, which is monitoring of the movements of the infrastructure, monitoring of movements, in vertical and in the horizontal direction, and monitoring is done with sophisticated techniques. And then once in a while they have to check the safety procedures, if everything is working correctly. They have to check the efficiency of the spillways. The spillways, you know, are much important because if you get a flood into the reservoir, then you must be able to release that water. Otherwise, if the dam gets surmounted in an unusual way, in an unpredicted way, then it's a problem, okay? So there are a lot of checks to be completed, and therefore getting also the permission to build them is much more complicated because there must be a national approval, etc. Instead, for barrages, the competence is at the regional level. It's the regional administration that is in charge of making checks because these are infrastructure that are less important. Even if, you know, if you reach a storage that is close to 1 million, still you have to be very careful because the potential consequences downstream of a failure, of course, they are potentially relevant. But this is our difference, and we concentrate on the barrages. And now let's classify also the barrages. And we can classify between regulated barrages, which are equipped with machinery like gates or regulated sluiceways to keep the upstream water level stable. And the reason why you want to keep it stable may be the need of withdrawing water with efficiency or navigation needs. On the other hand, you have the burden of the maintenance. If you have a regulated barrage, you have to check the gates, the functioning of the gates, you have to move the gates, and in a way you have to check that every maneuvering is occurring in safe conditions. So, and also they are more expensive to build because there are moving elements. And then there are the unregulated barrages, which are simpler. Regulation of the upstream water level is not done. So they are like fixed infrastructures. There is little things that are moving there. And construction is simpler. But on the other hand, you have the inconvenience that you cannot keep the upstream water level stable. So you have to take it into account in your design. And then there are temporary barrages. Temporary barrages are typically seasonal barrages. They are built during the low flow season, and they may be built by using stones that you find in place, and material, usually it's natural material, or they may be built by using bricks that are removed. And they are typically removed when you don't need them in the wet season, and which is also the season where you may have floods that may destroy these temporary barrages. There are still examples, especially in the Eastern world, where temporary barrages are frequently used. But I also see many temporary barrages in this region. And if you walk across along rivers during summer, you often find temporary barrages built by gravel, by earth and loose earth, and the scope is to divert a little amount of flow. For typically they are used for irrigation, but some of them are also used for very small scale hydropower plants and for producing, for instance, energy, electricity for a farm, for a single farm or a single house, etc. We will talk in specific of we will talk about fixed barrages, unregulated ones in specific, because these are the simpler one, the one that most frequently a young professional engineer may be asked to design. Here there is a figure which I think I already discussed with you. This is a Google map, and therefore you can enlarge it. And it's a barrage that is on the Danube, and it's a barrage which is conceived for keeping the Danube available for navigation. And I think I already discussed this with you, so I don't want to dedicate more time. I just want to say one thing that I didn't say, for sure I didn't say, and it's this purpose of navigating a river that leads to the construction of barrages. Most of the long rivers in Europe, the Rhine River, the Danube, and also the Sena River. Most of them are equipped with river barrages in order to make sure that navigation is possible. And in order to pass through them, there are navigation docks. You can see here the navigation dock on the left side of the river. The navigation dock allows boats to get into and out. Let me see if there is a link. I'm not sure. Let me see. No, I don't think I have a link here of how navigation locks work, but there is a nice figure. I think you know how navigation dock function, but there is a nice figure. Let me see if I can find it. I think it is in Wikipedia. Let me navigation dock Wikipedia. I think it's just give me 1 second. I think navigation. Let me see. There is a nice figure on Wikipedia which explains how they work, but okay, I'll tell you later because I can't find it now. Let me see, navigation dock Wikimedia. I think I found it on Wikipedia, so no, I don't think I can find it. I'll tell you later because I have it linked in another page. I have to link it here also. Okay, let me just show it to you after the break. So as I said, most of the European rivers are equipped with barrages in order to ensure navigation. The problem is that these barrages are a concern for environmental impact because they break, as I said, they break the river from an ecologic point of view. There is a break between the ecologic system, living organisms in practice, upstream and downstream. And also there is a slowdown of the river flow. The river flow velocity is decreased because you increase the storage in the river, and therefore there is a reduction of the velocity, which implies a reduction of the oxygen content of the water, and this causes a decrease of water quality. And again, it's a matter of concern. Also, there is the problem that these barrages, in a way, they retain part of the sediment transport, and they can cause siltation upstream and erosion downstream. I mean, as I said, these are a matter of concern. There is only one exception of long European river which is not equipped with barrages, and the exception is the Po River. The Po River has only one barrage, which is the hydropower plant of Isola Serafini, which we discussed some lectures ago. And as I said, the Po River is an exception. And there are discussions in Italy. They were more active in the past. Now it's not really a current discussion, but there were discussions on the opportunity to equip the Po River with additional barrages in order to ensure navigation and in order to produce hydropower. And the discussion was, you know, a little bit animated because we know now what is the effect in terms of environmental impact, and also we are concerned by the reduction of the delivery of sand to the river delta and then the Adriatic Sea. If you reduce the delivery of sand, there is the problem of sand deprivation in the sea, which leads to beach erosion. And beach erosion is a matter of concern in the Adriatic Sea for its impact on tourism and in a way, on the ecology, on the environmental state of beaches. So at the end, they didn't move forward. I mean, I think it was a right choice. Anyway, of course, the fixed barrages have not this problem because their scale is much lower. They look like a break in the river ecology, but the break is not as significant as for a huge barrage because the difference in elevation is limited. With a small barrage, you have between the water level upstream and downstream, you have a smaller difference, and therefore, you know, the breaking of the ecology is not so relevant. Okay, I think we can make a break here, and then we can start discussing the unregulated barrages. If you have any question, just let me know. Otherwise, we take 5 minutes break. Okay, here I am. So let's get again our web page. Very good. And now, river barrages. As I said, there is an application which is widely used for river barrages, which is, let me move this, okay, here. There is an application which is the small-scale hydropower plants. They are also called run-of-the-river hydropower plants. There is a Wikipedia link here. And the Wikipedia link is dedicated to run-of-the-river hydroelectricity. And it's called run-of-the-river. Let me see if there are other figures, because they use the water as it runs. And so there is no, or let's say no significant storage. Water is left running. So they are called run of the river. And this is an interesting link which you may read. And there is a figure here, for instance. This is a run of the river hydropower plant, which it's installed over a dam, but it's the run-of-the-river plant. They are placed in the part of the dam where water naturally flows during the whole year. And they also use the water that is flowing from upstream to downstream, so the water is retained and released just downstream. They use this water flow also to produce hydropower. Usually hydropower is produced by releasing water much downstream, because the amount of hydropower that you produce, as you may know, it's linearly proportional, is directly proportional to what is called the head of the hydropower plant, or hydraulic jump. It's the difference in elevation between the water level upstream and the water level, where water is released. So they tend to release water much downstream in order to increase the head, the hydraulic jump. But in some cases, we can also produce hydropower when the water is released immediately downstream. And in this case, we talk of run-of-the-river hydropower plant. This figure is another plant, which it's a floating plant. There is no water accumulation at all here. It's just placed, this floating plant, over the river. It's left floating, and it's not allowed to move downstream. So the plant is floating but fixed. And the movement of water through this floating body produces energy. There is a turbine inside which rotates and then producing energy. And there is a wire connecting the floating plant to the land, to the river banks, through which energy is then transmitted. So, going back to our river barrages, they are mainly used for this purpose, but also they are used for withdrawing water for irrigation purposes, civil use. So they can also be used for withdrawing water, for using the water not for hydropower, I mean for other uses. Also, we try today to give a multiple configuration to these barrages. We call them multiple use barrages, meaning that you can use water for irrigation, but also for producing power, hydropower, because if you use water for irrigation, usually you need to bring water downstream, and you could use this flow in order to produce hydropower. The main problem with the multiple use is not technological. I mean, it is relatively easy today with the efficient plants that we have to produce hydropower, even if the flow is relatively slow. So it's not a technological problem. It's mainly a problem of concomitance of the uses, because concurrency, because sometimes when you need water for irrigation, you don't need energy, because energy is more needed during winter and it's less needed in summer, for at least energy for civil use. And then it's the energy demand is not in phase with the water demand for irrigation. So it's just the fact that the irrigation plants are used in summer when we don't need much energy. So this is the main problem with the multiple use. And there are other uses for barrages and reservoirs, for instance, flood protection. And even in this case, we need to check whether it's the users are conflicting. The uses are conflicting. Okay, so we know how to use the flow duration curve to estimate the design flow of these barrages, because this is our first step. We have to estimate the design flow. Okay, and the design flow, we know how it's estimated. It's a cost-benefit analysis, basically. It is very often the design flow is close to the Q60 flow with duration of 60 days. And we already discussed about these indexes, so we don't discuss this anymore. Okay, and now we discuss instead the structure of the unregulated river barrage. Here there is, before I start by describing these parts of the structure, let me refer to this sketch. This is a typical sketch, and let me copy it, because I want to copy it and to bring it to the graphic blackboard. Just 1 second. Okay, here it is. So 1 second. Okay, let me paste it here. Let me see if I can. Okay, give me 1 second, because I still need to. Okay. Let's give some time to copy. Perfect, it's copied. Now I just have to delete this. Give me some time. Okay, and then just this. Good. So this is our figure taken from the website. Let me expand it a little bit. Okay. Good. This is what I wanted. Perfect. Okay, this is our figure. This is a scheme that is taken by a famous book that was published around 1970 by Giuseppe Evangelisti. He was a famous professional engineer and professor at the University of Bologna. He was expert in designing dams, hydropower plants, and river barrages. So I took this sketch from one of his books. It is a typical sketch. It's not the only structure that we can use. It's not the only scheme that we can use. This is a plant, it's a barrage that is developed in the longitudinal direction. there are also barrages that are more expanded in the transversal direction. This barrage scheme is typically used when you don't have much room on the side, on the banks of the river. And this is the typical situation that we get into the mountains. When you build a barrage in a mountain river, usually you have the hill slopes, the banks that are very steep, and therefore you cannot get much room there. And for this reason, you need to elongate the structure in the longitudinal direction. So this is then a structure that you could use in mountains, typical structure. I think it is meaningful because it allows us to describe the main features of a river barrage. So let me just draw something here. And first, the river is flowing, as you see, from the left to the right. Okay. The red arrow, and now I put, sorry, the black arrow, now I put another one, a red one, shows the direction of the water flow. Upstream is left, downstream is right. First of all, a barrage must be able to let the flood flow pass through without significant impact in terms of water level upstream. Okay, and this purpose is achieved by a spillway, which is called the main spillway. The main spillway must have a size and an elevation such that the flood water level upstream is not much increased. In any case, keep in mind that when you design such a plant, any administration that is responsible for giving you permission asks you to make an assessment of the undisturbed water level during floods and the water level after the construction of the barrage. So they ask you to assess changes in water level through the analysis of the water levels during floods, and this is done by integrating the Desenvenant equations. If you had some background in fluid mechanics, you for sure remember what the Desenvenant equations are. And I'm not discussing about integration of the Desenvenant equation. I'm just saying that there are commercial softwares that allow you to make this assessment, commercial and non-commercial. I just want to give you an example. As I said, it's something that is not related to this course. I don't ask anything at the exam, but I want to give you an example of such a software, which is widely used. It's the ECRAS software. I'm searching in Google. This is, I searched in Google for ECRAS, as you see up there. And here there is the downloads, the main page. This is a very nice software. It's free. It's not open source. I clicked on it, but I can't. Okay, here we are. And it's, as I said, it's very nice. It allows you to make an assessment of water levels. I think it allows also you to make a 2D simulation, two-dimensional simulation. Nothing to discuss within here. I just wanted to tell you because this is easy to download for any platform, and you can run any simulation that you wish in a relatively simple manner. But you need to know the theory, because the software, like any software that applies complex equations, may have some bugs, may be unreliable in certain cases, and therefore you have to know the theory behind if you want to be able to assess reliability. Okay, let's close this page. It's not our aim, as I said. Okay, so the main spillway, it is to be designed in this way. Another fundamental element here is what's called the environmental flow spillway. This spillway is dedicated to ensuring that you have downstream a minimum flow in any condition, any. I mean, when you are taking water, when you are not taking water, the structure should be such that, without any regulation, because this is an unregulated barrage, such that downstream we have in any condition a minimum flow, unless there is no flow incoming upstream. Of course, if from upstream you don't have any flow, then you cannot release anything downstream. But in all the situation in which you have some flow coming from upstream, then you have to release the environmental flow. Keep in mind the fundamental difference. In dams, when you have a reservoir upstream, you must release the environmental flow in any condition, even if there is no inflow into the reservoir, okay? So even if there was no inflow in natural condition, when you build a reservoir, you must make sure that there is environmental flow released in any condition, unless the reservoir gets empty or very extreme situations. For river barrages, given that we don't have any accumulation of flow, then it means that if you don't have any inflow upstream, you cannot release the environmental flow. But in any other conditions, you must make sure that there is the environmental flow downstream. Where do you get an estimate of the environmental flow? From the laws in force. So you have to look at the laws in force in the country where you work and make sure to get the updated and current rules for estimating the environmental flow. In Europe, it's compulsory. So there is a European directive that prescribes that any intervention on rivers must be accompanied by an estimation of the environmental flow and appropriate measures for making sure that it's always released. Okay. The fact that there is, sorry, I just want to look at the chat to make sure that I'm not missing your question. Yes, environmental flow is equal to the flusso minimo vitale. You know, in Italy there is a discussion because the flusso minimo vitale, it's a term that is outdated. People are still using it. In fact, the acronym in Italy is still DMV, but it's an outdated term because it gives the feeling, the flusso minimo vitale, that you release just the amount of flow that is necessary in order not to die. And it is a very negative message that you deliver if you say the flusso minimo vitale. You give the feeling to stakeholders that downstream you have really a kind of crisis, that fishes are close to die, everything is close to die. And so it is caused also in Italian now, the flusso ambientale or something like that, so which means environmental flow. And sometimes they call the flusso ambientale, or they call I can't remember in Italian, there is another term that is used, but I can't remember it now. I cannot switch easily. Yeah, ecologic, yeah, the flusso ecologico, perfect. Thank you very much. And it's more meaningful. It's not just a matter of communication, because actually the way it is estimated today in compliance with the European directive, it's make sure that you don't release just the minimum flow in order to survive. It's some more. So it's more meaningful if you don't call it the flusso minimo vitale. But still, there are many people, many written documents that are using this terminology, which doesn't exist in the English literature. It doesn't exist something like vital minimum flow. It doesn't exist. So, as I said, the fact that there is a European directive doesn't imply automatically that all the member states are complying with the directive, because usually directives give a deadline for compliance, for adapting the national laws in compliance to the directive. So most of the countries, especially those who are members of the European Union since a long time ago, they basically complied, but it's not automatic. In general, for European directives, it's not automatic. Still, even if the law enforced in the given country doesn't prescribe it, it's now an international standard that is internationally recognized. So it's something that you should estimate. There are also international guidelines. And what is the order of magnitude? So there are some rules of thumb. And one rule of thumb, I'm not sure it is written in my webpage, is Q355. So it means, as you know, flow with the duration of 355 days. This is a first rule of thumb. A second rule of thumb, which is, I mean, in the past was widely applied, is 2 liters per second per square kilometer of upstream catchment. I repeat, 2 liters per second per unit square kilometer of upstream catchment. And usually it's in most of the cases is close to Q355. It's interesting because, you know, rules of thumb have very frequently a physical motivation, a physical justification, and the fact that sometimes they give similar estimates means that there is indeed a physical motivation, justification behind. So the fact that the environmental flow must always be ensured, yeah, it depends, Maurus. It depends. I mean, what the orders of magnitude that I gave to you are to be taken as minimum numbers. So I'm not surprised if somebody talked about Q335 or 47. I'm not surprised. First of all, keep in mind that in many rivers it's not a huge difference. It depends, of course, on the shape of the flow duration curve, but usually in the right tail is quite flat. So it doesn't really change much. If you think about 8 days of difference in duration, it's nothing in low flows. In high flows, it's a different story. But in low flows, it's as you remember, the shape of the flow duration curve. It's not steep in the final part. Usually, not always. And so I guess that they update these estimates because what I'm talking are rules of thumb that refer to the flusso minimo vitale concept. Okay, good. And there is a question on the chat. I have a question about the situation or the location. What guides the choice of selection for where to situate the barrage? Yeah, I think I am discussing it later, but I want to anticipate the reply. And there are several issues to consider. First of all, where you need the barrage, because when you build a barrage, you build it for some needs, which may be hydropower or maybe irrigation, maybe civil use. So usually it's much better to locate the barrage close to the use for obvious reasons, and because otherwise you need long structures, long infrastructures to deliver water. And if the travel is short, you have less leakage. So there is, let's say, an economic, but not rather a social motivation to consider, a social consideration to make about the best location. And then after the social considerations, you have to make some technological considerations like is it feasible from a technological point of view to locate the barrage much upstream? Is it possible to build a pipe that is, I don't know, 100 kilometers long or not? And this is a technical consideration that involves several aspects. And then there is an environmental consideration, like do you have enough water where you want to build the barrage, or should you go upstream where there is typically more water? Why there is more water upstream? Because you have less evaporation, you have less infiltration, and you have less other uses. So if you get water before others, of course there is more water. Of course it's not possible. In some cases they don't give you the permission, because if your infrastructure undermines or gives some negative impact on other users, they may not give you the permission. But in any case, there is an environmental consideration to make, and also there is the environmental impact. So if you go upstream, the environmental impact may be higher or lower. It depends. It depends on the situation. So there are several considerations to make, but usually, first of all, you have the societal and the technological considerations. Also, the shape of the river. Like when the river is very large, it's not really convenient. If you are a river that 1 kilometer large, it's much better to go in a place where you have a natural restriction of the cross river section. Especially if you want to build a dam, you need a natural, let's say, configuration that allows you to fix the dam to the hill slopes, to hold the dam to the hill slopes. So, I mean, usually you have a prevailing technical societal consideration, and then there is the environmental impact assessment. Also, there is the impact on people, and it's a societal consideration. If you build a dam, you know, there are a lot of impacts. There are people that may get flooded. You have to relocate them. So very often they say, let's move upstream, because upstream there are no people. So, as I said, several considerations. And let's go back to the environmental flow. Given that it must be always guaranteed, then it follows that the environmental flow, the spillway of the environmental flow, so the environmental flow spillway, is located at an elevation that is lower with respect to the other spillways, because it must have the highest priority. And priority in terms of flow means that if you have a spillway, priority means elevation. So the lower the spillway, the higher the priority. So you must make sure that you get first flow through the environmental flow spillway, and then flow through the other spillways, which means that the elevation of the environmental flow spillway must be lower than the elevation of the other spillways. And let me draw something here. Like if you draw a section, sorry, I was using the wrong pen. Let's make a section here. And let's look at this barrage from downstream to upstream. And what you see, let's look on the right, is that you have a shape of the cross river section that may be like that. And then you build your spillway. It's, I mean, not easy. So there is a first part, the wings. You see the wings are here. Okay. So you have a wing here, and then there is the main spillway, and then here you have the environmental flow spillway, and then again the wings. Okay. And of course, when you get a water level upstream, that it's like here, you don't have any flow through the main spillway, but you have some flow through the environmental flow spillway. And then on the side, there will be the diversion spillway, which will be located more or less at this level. This is the diversion spillway, which is here. Okay, so elevation of, as I said, elevation of the environmental flow spillway is the lower one. And a big question, of course, is a question is, what is the difference in elevation, delta H, between, let's see, let me get another color, this difference in elevation here, okay, between the environmental flow spillway, the diversion spillway, and the main spillway. There must be a difference in elevation, so there is a difference here, delta H. This is called, in my webpage, I think it's called delta H1. And then there is another difference in elevation, which is the difference in elevation between the diversion spillway and the main spillway, delta H2. So a technical question which we will discuss soon is what is the amount of delta H1 and delta H2. Okay, good. Now, given that I hope we understood that the environmental low spillway is at the lower level, Then let's discuss what are the wings. The wings are a kind of link between the main structure of the spillway and the hill slopes. If I look at the transversal section on the right, actually I put the wing between the hill slope and the environmental flow spillway. And while here you see that the wing is located between the main spillway and the environmental flow spillway, it's just a matter of a different positioning. It doesn't make a big difference. What is important is to clarify the role of the wings. The role of the wings, whose slope is it may be about 45 degrees. So this is about 45 degrees. And the purpose of the wings is to keep the main flow, and in particular the flood flow, far from the hill slopes, to concentrate the main flow in the middle of the river, to avoid riverbank erosion. Okay, so fixed barrages of any type usually are equipped with those wings to concentrate the main flow in the middle of the river. Okay, and then let's talk about the diversion spillway. What is the purpose of the diversion spillway? It's to divert water, it's to take water. So we have some flow from the river that is going here, okay? And the purpose is to bring this flow downstream along another way, which is not the river, okay? And here I put two spillways, two diversion spillways equipped with a gate. What you see here with the circle, this symbol here, which I am now depicting in red, it's a gate, okay? I'll show you later some images of gates to better understand what they are, but the purpose of the gate is to stop the flow. And we need to equip any diversion spillway with a gate, because for cleaning, for maintenance, we may need to stop the inflow into the series of structures that bring water downstream. The main spillway shouldn't be equipped with a gate for obvious reasons, because we need to get it clean to allow the transit of the flood flows. This is an unregulated barrage, which means that we don't have to put there any mobile gate on the main flow. The main flow is unregulated. Of course, the withdrawal may be regulated, but when we refer to unregulated, we mean the main flow. It's not regulated, okay? So we cannot have gates on the main spillway. Also, we cannot have gates on the environmental flow spillway, because usually they are not allowed by the local administration, because, you know, you cannot close the environmental flow. You cannot, okay? So it's unusual that they allow you to put a gate there. It may happen in some particular situations for other reasons, but not for blocking the flow, okay? What could be the other reasons? We will discuss fish ramps, which allow fish to move from downstream to upstream through the barrage. If you get too much water in the fish ramp, the fishes doesn't have strength enough to swim upstream, and therefore they may allow you to reduce for this purpose the flow through the environmental flow spillway, but just for this purpose. They won't allow you to completely close it, okay? So the diversion spillway, as I said, has a gate, and there are usually two of them. Two of them because it may be that, given that you put gates there, it may be that one gate fails in moving. It may be that you try to move a gate and it's not possible because there are some some mechanical problems, and therefore with 2 gates you can reach a more refined regulation. Soon after the diversion, you have a gravel trap. Gravel trap, the purpose is to trap the gravel, okay? And therefore here you have this kind of step. It's a step which separates, it's a bottom step, okay? Separates the gravel trap from the subsequent pool, which is the sand trap. The purpose of the gravel trap is, of course, to trap the gravel, so material of larger size. The purpose of the sand trap is to block the tiny material. Okay. Why do we want to remove gravel and sand from water? The reason is obvious. When you bring water downstream, usually you have mechanical parts. Either they can be turbines, or they can be pumps. It depends on the use of the water. So you cannot tolerate that you have solid material into the water up to a certain size. Usually, depending on the mechanical parts that you have downstream, you have a limiting situation, a limiting condition. Like the turbine usually can allow solid material up to the size of 0.3 or 0.8 millimeters. And then you have to make sure that the material of higher size, larger size, is trapped and removed, okay? And it's more efficient if you remove by class sizes. So first the gravel and then the sand. Okay, and then the gravel trap must be cleaned. And in order to clean it, you get flushing sluiceways to allow water, when you open them, to flow back to the river. And if the flush is with high velocity, then it helps in removing the gravel and bringing the gravel back to the river. So periodically, once in a while, we need to go there, and you don't deliver water downstream, but you use the water that you withdrew in order to flush these pools. And the same, there is another flushing sluiceway which is placed there. What is a sluiceway? A sluiceway, usually it's an aperture, it's a window that is placed in the bottom. And usually you have their roof, the higher part of this way out, it's below the water level, and then they are called sluiceways. Okay, and then the sand trap. Again, there is this step which separates the gravel trap from the sand trap, and its elevation is usually about 50 centimeters. In order to divide these pools, in order to not to allow the gravel to move to the sand trap. And then there is the sand trap. Usually it's separated into 2 channels in order to allow cleaning and maintenance without interrupting the flow downstream. And keep in mind that the sand trap is to be cleaned more frequently than the gravel trap usually, and this is why usually the sand trap is articulated in a series of pools in parallel, so you can clean them continuously. Okay, and you must make sure that there is a top spillway, which is here, in order to make sure that there is any overflow can be evacuated back to the river. So this is our top spillway. This is not a sluiceway, it's a top one, which means that it can be activated only when water reaches an emergency level. And you have to make sure that this structure is not flooded. So it must be, you must create the conditions, safety conditions, so that the structure is not flooded. Because, you know, if you get this overall structure that is flooded, then probably this would imply a significant damage that you want to avoid. Okay, and then there is here another step downstream the sand trap. It's a bottom step in order to keep the sand inside. And then there is here an upstream tank. What is the purpose of the upstream tank? The purpose is in case you have a pipe to the water system, okay, downstream, you can deliver the water by using a pipe or using a channel. So if you use a channel, an open channel, actually you don't need an upstream tank. But if you use a pipe, you have to avoid the entrance of water into the pipe, and the entrance of air, because the presence of air into a pipe in pressure implies some impact on the structure of the pipe, because it causes a series of vibrations which you want to avoid. So you have to make sure that there is no air in the water, and therefore the purpose of the upstream tank is to make sure that you have the water level that even in minimum conditions is far above the roof of the pipe. Okay, so you have to make sure that the entrance of the pipe is always submerged, and this is the purpose of the upstream tank. Okay, and I think I discussed more or less everything, and here you see the foundations. It's the dashed line, and it can be either a foundation binding the structure to the bottom of the river, but it may also be equipped with lateral bindings, meaning that the wings can protrude into the hill slope in order to make sure that the whole structure is not slided downstream. So you have to make sure that the structure is well anchored, well fixed to the river bottom. Okay, I think I described everything. Now let's go to the technical parts. And the technical parts are, first of all, what is the first thing that we have to discuss? Given that the environmental flow spillway is the lowest spillway in terms of elevation, what could be the elevation to which we place it? This is the first decision. So how much tall should be this structure? This is the first technical consideration. Okay, I propose now to make the longer break and then we can continue our discussion later. Any question? It may be that there is a question on the chat. So it may be that the sand trap gets full, but you should avoid it. I mean, it should be cleaned at a frequency that allows you to make sure that it doesn't get full. Because if it gets full, you know, if there is sand entering into the pipe, this is another problem, because the presence of sand in the pipe can cause problem to the machinery that is located downstream, but also to the pipe, because there is a kind of erosion, of progressive degradation of the pipe for the effect of the scrapping of the sand, you know, and which is something that we have to avoid. And of course you use monitoring systems when there is the possibility to monitor the sand level, and when you see that there are also automatic systems that open the flushing sluiceway once that the sand reaches a given level. It can be done automatically. Okay, good. Let's break for 15 minutes. So at 11:10. Okay. Let me see. Okay, how many we are? Okay, so as I said, let me check the web page. I want to see whether I forgot something. Yes, something I forgot. Okay, good. So Okay, let me go back to the blackboard. Here we are. Okay, so I forgot just to say one thing. I forgot to talk about, it's quite trivial, but I forgot to talk about these protections from erosion that we place downstream. There are several ways for protecting downstream from erosion. We need to protect downstream for the impact of the flowing water. Usually water falls from the spillways, and therefore there is the possibility that we get kind of holes there, erosion. And also there is to say that given that we trap the material, the sediment transport, it is trapped by the barrage, then downstream there is the risk of getting an erosion. I just wanted to show you, if you give me 1 minute, I just wanted to show you one picture because it is impressive, and it is impressive to see to what extent we can get erosion downstream. Let me open 1 second. Let me open up my file manager. I wanted to check if I can find some picture that I took during a trip with the students. So let me see. Give me 1 second. Let me see. Okay. It's not here. So let's see. No. Maybe it's here. No. Or here. Let's see. No, they are not here. Okay. Nothing to. No hope. I wanted to get. So if they are not here, okay, maybe I can find them. 1 second. I need to go back in time with my picture. Give me 1 second. I think. No, not here. Let's see if it's here. No. Otherwise, I show you next time. But I still have some hopes. Let me see. Okay, I found them. Good. So, okay, let me show you these pictures. Okay, this is the Secchia River. It's the boundary. It's located at the boundary between my local municipality, Reggio Emilia, and those of that of Modena. This is a river that flows from the Apennines in the south-north direction. It's a tributary of the Po River, and I went with the students and I show you some pictures because here they built in the past a barrage in order to derive water for irrigation. This is a barrage. The storage upstream is about 1 million cubic meters, so it's a limiting situation, but it's not a dam. It's classified as a barrage. And as I said, water is taken for irrigation. The problem that they got here is that the barrage was siltated, was filled by sediments in a very short time, like 3-4 years. So 1 million of cubic meters of storage was brought to 1/3 in a time lapse of no more than 3-4 years. So they had to renovate, to make some works in order to make sure that the accumulated material upstream was brought downstream. It is not easy. It is not easy because it's not just enough that you open the sluice ways. If the extension of the reservoir is large, if you open the sluice way, you get downstream only the material that is very close to the sluice way that you open, but the material that is settled down upstream, it remains there. Also, there is the problem that if you release sediments downstream suddenly, there is a huge environmental impact because the turbidity of the river flow increases, and this is really harmful for fishes, etc. So the process must be managed, must be a slow process, this process of bringing material downstream, and managed in some way. So what they did here is to try to build some infrastructures that allowed them to shift the main flow inside the reservoir from the left to the right to the center. So they were able to manage where the main current was flowing in order to clean subsequent portions of the reservoir, and they were building here these infrastructures. The purpose is first to clean the reservoir upstream, but also to reduce the erosion downstream, because the collection of the material upstream increased the erosion downstream. And I want to show you some pictures which it is interesting. And okay, this is the river. This is a part of the reservoir where they built these new infrastructures. And I'm just going through the pictures. And here you see downstream. What you see in the upper part of the picture is the main barrage. The main barrage, so the river is flowing from the left to the upper part of the picture. And upstream, the main barrage, you see there is the reservoir that is now empty, but you see a lot of material that is accumulated there. And the purpose was here to be able to shift the main stream in order to, as I said, to be able to clean the different and subsequent portions of the upstream reservoir. This is the fish ramp. I am on the main spillway here, on the main barrage, looking downstream. And this is the fish ramp. There was some snow. It was during spring. It was 2012 here. And again, this is the fish ramp. You see, the fish ramp is made by subsequent pools. And we will talk about fish ramps later. And this is what is called the subsequent pools. It's called, okay, I don't remember the technical term. Let me think about it. But it's made by subsequent pool. Okay, I tell you. And here it's from the main barrage to upstream. And you see the upstream catchment also, from which the Apennine up there with the snow. And again, another picture. And here you see downstream what happened. I am here on the main barrage looking downstream. Downstream, there is the bedrock that emerged because of the erosion. So before building the barrage here, there was gravel. But now with the barrage trapping the gravel, then the bedrock emerged. And downstream the bedrock, where the material, the riverbed, was more erodible, you will see that a kind of canyon emerged. And this is again the fish ramp with less water, okay, because they closed it in order to let us see how it is built. And this is a downstream barrage that they built because they wanted to limit the erosion downstream. They wanted to contribute to limit the erosion. And you see that it is protected by sheet piles. What you see on the opposite side of the river, this kind of brown piles, they are sheet piles, which are, the purpose is to protect the banks of the river, because the problem is that the erosion also undermines the stability of the banks. And here it's another detail. Again, and let's look what happened downstream. You see downstream what happened. There is the clay material. The clay was completely eroded, and the height of this of these vertical walls is something like 5-6 meters. In some cases, they reached a height of 15 meters. So it means that the riverbed went down. Keep in mind, this barrage, we were in 2012. It was built in 1980, so 30 years before. In 30 years, they developed an erosion in some part of the rivers of 15 meters. And you see again another figure. You see the canyon downstream. And if you look on the right of the picture, much downstream, you see that indeed they are quite high. This is another detail. These are the students. And again, the barrage, the upstream. You see in the upper part of the picture, you can see, it is very tiny, the main barrage. It's upper left. Just below the sky, you see couple of centimeters below the sky on the left of the figure. You see, you can just see small portions of the main barrage. Here are the students. Okay, and this is an hydropower plant that is located downstream. I think I can close it. So, erosion, we were talking about erosion. So, of course, here the protection is just limited to protect a few meters downstream because this is the purpose of the sketch here. But you may need to protect, as we have seen, the riverbed for a long extension, maybe with other small barrages located downstream to fix the elevation of the riverbed. The protection that you put immediately downstream a barrage may be done with rubber mound, so boulders. Okay, so you can just put boulders there, and or you may put some protections in concrete. We don't go into the details. I just wanted to mention to you that we need to protect downstream from erosion. Okay, good. Now let's go to let's talk about elevation again, elevation of the spillway. So elevation of the spillway, as I said, let's refer to the environmental flow spillway, which is the lowest one. And so how can we determine its elevation? First of all, we need to make a survey of the undisturbed riverbed, so we have a clear knowledge of the shape of the river, where we want to build the barrage, upstream and downstream. For a convenient extension, we need to get the longitudinal profile of the river, an idea, and of the cross river section. So we need to know the geometry of the riverbed for a convenient extension, upstream and downstream. Also, it is necessary to assess, to study the water profile during floods, which I mentioned and discussed it before. Now, if you increase the elevation of the structure, there are some positive effects. The first positive effect is that you increase the storage upstream. Of course, if you need to get water from a river, the larger the storage and the better it is, because if you have some storage, you can compensate, you may compensate, shift between water flow, natural flow in the river, and water demand. So if you have for some hours during the day the demand that is exceeding the flow, you can compensate with storage. So you may have the opportunity for some compensation. Typically, with these barrages, we look for a daily compensation. So if you have an idea of the progress of water demand during the day, and you have an idea of the water flow in the different seasons, then you can get an estimate of the volume that you need to compensate. And then you may increase the elevation of the spillway of the barrage in order to create the desired storage. Also, there is the benefit that if you increase the elevation of the barrage, you may decrease the frequency of upstream dredgings. Periodically, you may need to dredge the reservoir upstream because, of course, you have to remove the material that is accumulated. And if you have a larger storage upstream, you can decrease the frequency of dredging. Dredging is always problematic because you know you have to very frequently you have to interrupt the water withdrawal, and you require machineries to do that. So if you decrease the frequency, of course, not too much, but if you decrease the frequency, it may be convenient. And also the barrage, it's more resilient with respect to extreme events, because of course if you have a little storage upstream, then it may suffice, I mean, a small event, a small flood event, a not very relevant flood event, to bring enough gravel into the upstream reservoir that you need to dredge, and you cannot operate the barrage anymore. If you have a larger storage, then usual events are not able to fill completely the storage, so the whole structure becomes more resilient. So you may want to increase a little bit the elevation of the barrage for this reason. On the other hand, you have to consider some downsides, which are the elevation of the water level upstream, and the environmental impact, and the cost of the structure, and the fact that you cannot exceed 15 meters. So it's something that you have to evaluate and make a cost-benefit analysis. And then, basing on your estimate of the storage that you want upstream and the overall elevation of the structure, you fix the quote, the level of your environmental flow spillway. Okay, and then, basing on that, we need to define the elevation of the other spillways. So how can we do that? So let me create a new, let me create a new page, or let me shift this, just one second, oops, just one second. Okay. Okay, good. Now, one second that I good. Okay, let me try to write here again a cross section of our barrage. So this is a hypothetical river cross section, and let's draw our barrage here. One second. So let's suppose that it's done in this way. I need to learn how to draw straight lines, so just one second, you have to be patient with me. So let's suppose that it's then we have the wings, and we have the main speedway here. One second. Main speedway, and then let's suppose that here we have the other wing, and then the environmental flow speedway, something like that, and then the wings again here. Okay, good. So let's suppose that is something like this, and then there is a difference in elevation here, which is, let's call it delta 1. Okay, delta H1. Okay, and then there is somewhere here, 1 second, somewhere here, the water diversion spillway, and then I need to, sorry, because delta H1 is not the, oops, delta H1, I am just building the figure, give me 1 second. Okay, delta H1 is not this. Okay, delta H1 is this one. So good, and then let me put let me just 1 second. Okay, and then delta H1 is here, and then we have delta H2, which is this one. Okay, delta H2. So we need to estimate these two differences in level. It's the difference between the elevation of the environmental flow spillway and the diversion spillway. So this is diversion, and this is environmental flow, env flow. So we need to estimate this elevation, and we need to estimate the difference in elevation delta H2 between the diversion spillway and the main spillway. Sorry, it took me some time to draw it. And how to estimate then delta H1 and delta H2. And sorry, this is our question. This is our question. So how to estimate delta H1? Don't understand why. 1 second. Delta H1. Okay. And how to estimate, it's not delta delta, but it's delta H. And how to estimate delta H2. Okay. So the key for estimating these differences in elevation is the general formula that gives us the flow through a large width spillway. And it's called the large width spillway. It's called Barrages, Barrages Spillway. So the Barrages Spillway. The formula through a Barrages spillway, it's of the flow through this spillway. Keep in mind the Barrages is a large width spillway, and the formula Q is given by a flow coefficient μ, and this is equal typically to 0.385, and then we have the width of the spillway L, which is in this case L, for instance, is given by this. If you look in the upper part of the picture, μL times the square root. Oh, sorry, I forgot an h before the square root. μLh, I will explain to you what h is, times 2g again h. So what is h? H is, let me draw now a sketch a longitudinal sketch of a spillway. If you have a Barrages spillway, it's a large width, it's a large length, let's say, because width can be measured in the longitudinal direction and on the transversal direction. The L that I put in this relationship, this L here, is measured in the transversal direction. And when I talked about the large width of the Barrages spillway, I was talking about the width in the longitudinal direction. So in this case, in the sketch that I'm drawing here, this is longitudinal direction, okay? Perfect. So if you look at the spillway, let's suppose that you have some water coming from upstream. Then what happens is that in correspondence of the spillway, you have a so-called call towards downstream, and this is what happens to water elevation. So you have a decrease of the water level over the spillway because of the increasing velocity of the flow that originates a call of water downstream. And then you have downstream, you have the flash of water. Okay, what is H? H is the difference in elevation between the elevation of the spillway and the undisturbed water level upstream. So this is my H. Okay, and so look at this relationship here. Okay, the Barrages relationship. And this is the key for us to estimate delta H1. And you can rewrite this relationship in this way. Q is equal to me L H to the power of 1.5 and 2g to the power of 0.5. Okay? Okay, very good. Now, let's suppose that we refer to our environmental flow spillway, and let's suppose that our Q now becomes QDMV. Oops, sorry. View. Okay, so let's suppose that Q becomes our QDMV. And let's suppose that instead of L as its meaning that you can see above here, L is the green one here, okay? And let's suppose that now our H in this relationship, so let me look at this H here. Let's substitute it with delta H, 1. Now, if we modify the formula in this way, it describes now the flow through the environmental flow spillway when I have precisely through it the DMV, so the environmental flow. So now I have, if you look at this relationship now, I am just putting a green framework to identify it. If you look at this relationship now, it is describing what happens in the environmental flow spillway when you have precisely the environmental flow flowing through it. So you have the environmental flow QDMV, which is given by the product of the flow coefficient μ, and then the width L of the spillway, delta H1 to the power of 1.5 and square root of 2g. So from this relationship here, now I can get an explicit relationship for delta H1. Let me write it on the left here. Delta H1 is equal to Q dmv divided by mi L square root 2g. I think it's okay, perfect, to the power of, so this would be 2/3. Okay, so this is an explicit relationship for delta H1. What is delta H1? It is our desired difference in elevation between the environmental flow spillway and the diversion spillway. Why? Because we want to make sure that the diversion is activated only after making sure that we have enough environmental flow downstream. So we don't want any diversion until we have made sure that downstream we have the environmental flow. And therefore, in order to activate any diversion, we have to make sure that the difference in elevation between the two spillways is at least and precisely delta H1 here. Sorry. Okay, why is this? Because until we don't reach the elevation of the diversion spillway, we are fine. We have no diversion. And when do we reach the elevation of the diversion spillway? We reach it only when the water level in the environmental spillway, I am highlighting it in blue, is equal to delta H1. And when we get a water level in the environmental spillway of delta H1, we have Q dmv downstream. So this is perfect, okay? In a similar way, I hope it's clear what I did here. In a similar way, we can estimate our delta H2. I put a blue, let me use a different color, sorry. Delta H2 in a similar way, because the reasoning that we make is the same. So when do I want to activate the main spillway? Only after I got QDMV from the environmental flow spillway plus the design diverted flow through the diversion spillway. And therefore, the elevation difference, delta H2, between diversion spillway and main spillway must be such that through the diversion I am getting my design flow QD. Okay, and therefore I am writing here in red my delta H2 will be equal to design flow QD divided by mi LD. LD is the overall width of the diversion spillway. If we have more than one, we sum all the individual widths. And then here I have the square root again of 2g to the power of 2/3. Sorry. I need to learn how to use this pen. There are too many buttons on the body of the pen. I have to deactivate them. Okay, this is our relationship, which I am now marking in 1 second in yellow. This is our relationship for delta H2. Okay, so what is the sequence of our events which I'm trying to describe? I have, first of all, me write in red. First of all, one environmental flow. Environmental flow. Okay, and sorry. Environmental flow. Good. And then second, I have delta H1. Okay, this is the level of water over the environmental flow. And then it follows that we have withdrawal or diversion. Let me call it diversion to be coherent. Diversion. Good. And then it's not well written, but good. And then 3, I have delta H2, and then I have the main spillway, which is activated. This is the sequence of events. Is it clear to everybody what we did, and is it clear how delta H1 and delta H2 were determined?
I did not understand delta H2.
Okay, perfect. So I assume that you understood delta H1, okay?
Yes.
Okay, perfect. So once that we get to the level delta H1, we start diverting flow, okay? And then it means that over the diversion spillway, you have an increasing water level. Let's suppose that flows from upstream increases, and then it means that you reach the level of the diversion spillway, and then diversion starts, and if you have yet an increase of water level because you have water flowing from upstream, for increasing water level over the diversion spillway, you get increasing diverted flow. At a certain point, you reach the, look at what I painted now, you reach through the diversion spillway the level of your design flow QD. At this stage, you don't need to divert water anymore. If you have a further increase of water level in the upstream reservoir, you need to evacuate the excess water in another way. And the other way is the diversion spillway. So the elevation of the diversion spillway should be, the elevation again of the diversion spillway should be higher than the elevation of the diversion spillway, with a difference in elevation should be higher with the difference in elevation that is delta H2. Delta H2 should be such that through the diversion spillway you get a diverted flow QD according to this relationship here that is circled in yellow. I'm not sure if I could be clear this time. So you use the same relationship. What is different, the same as for computing delta H1. What is different is the level, the amount of the flow. For delta H1, you have to use QDMV as flow through the spillway. For delta H2, you have to assume QD, the diverted flow. And basing on the diverted flow, you place the elevation of the main spillway. I think if it is not clear, please tell me because I make another sketch. It's easy for me to remake it. Would you like I expand what you see here in a dedicated sketch? It's no problem. How do we, please tell me, would you like I expand it?
Yeah, please.
Okay, perfect.
I think that would be more clear. Thank
you.
Yeah,
Perfect. So, and first of all, let me reply to the questions on the chat. It's how we define QD, the diverted flow. It is defined, it's the design flow of your withdrawal. It's defined through the flow duration curve. Okay, and okay, Now let me get another one. Sorry. Okay, perfect. Give me 1 second. I do. Okay, let me try to do this way, and I hope it's clearer. So we have the elevation of the environmental flow speedway. Good. And then we have here, let me put it with another color. We have here the diversion speedway. And then we have here in red the main speedway. Okay. Now let's suppose that you get water level here which is precisely at the elevation of the main speedway. This is upstream water. Okay, and let's suppose that we get another upstream water 2, and let's suppose that we have another water level now which is here, okay, which is upstream water 1. It is just a different water level, upstream water 1. Okay, now what are these two water levels? Are upstream water 1 is the level of activation of diversion, okay, and upstream water 2 is the level of activation of the main spillway. Now let me call this elevation delta H1, and the river flow that is coming out from here is QDMV. Okay, now let me now call this difference in elevation here delta H2, and the flow that is coming out from here, that this is my QD. Is it clear, the sketch? And first let's focus on the situation when the water level is 1, upstream water 1. In this situation we need to make sure that for the elevation delta H1 we get a flow which is equal to QDMV, and the way we get it is delta H1 is equal to, I rewrite because for clarity, QDMV divided by me L square root 2G to the power of 2/3. So when I have, and this is valid for upstream water 1. This is valid for upstream water 1. So when I have a level corresponding to upstream water 1, I have an elevation over the environmental spillway of water equal to delta H1, and in this situation I have through the environmental spillway a flow QDMV. I hope this is clear. And if not, just stop me. Now, let's refer to a different situation. I have a water level which is equivalent to upstream water 2. And let me focus only on the diversion spillway. What happens in the diversion spillway? I have a flow through the diversion spillway. This flow is equal to QD. It's a design flow. And what is then the elevation delta H2? It is given by delta H2 is equal to the flow at the numerator, and the flow in this case is QD. It's my diversion flow. At the denominator, I have again me L square root of 2G to the power of 2/3. So in this situation, with an elevation of delta H2, I get through the diversion spillway, I'm getting QD. Now, I don't need any more water through the previous spillways. So let me put the main spillway at that elevation. That's it. Is this clear? If it is clear, I have a final consideration to make.
I have one question.
Yes, please.
For delta H2, I don't really understand why it's only QD and not QD plus QDMV. Because at the same time, while I'm diverting QD, I still must make sure that QDMV goes out, right?
Yes, this is right, but I am focusing only on QD because I am focusing on what happens on the diversion spillway. When I made my explanation, I said, let's focus only on the diversion spillway. What happens there? Let's forget the environmental flow. For sure, you are right. There is still environmental flow that is going out. And the reason why I didn't say this is because I have something more to say. So, but now I want to make sure that you understood what happens over the diversion spillway. Let's suppose that you don't have any problem with upstream flow. So you can have enough flow from upstream to feed the diversion spillway and the environmental flow spillway. Let's just focus on what happens on the diversion spillway. And I want to make sure that you understand that with an elevation of water over the diversion spillway equal to delta H2, you are getting QD through the diversion spillway. So this is what you need to understand now. So if you understood this, now let's focus on both of them. Okay? So, I mean, if you understood what happens on the diversion spillway, what happens on both of them? Okay, what happens on the diversion spillway? We already understood this. What happens on the environmental flow spillway? You have a flow through it which is higher than the environmental flow. Because the flow through the environmental flow spillway is given by, let's call it QA, okay? Just to use another symbol, is given by simply me L. L is the length, is the width, sorry, of the environmental flow spillway. Oops. I forgot to put here H, just 1 second. Okay, me L. Now, again, now here we have delta H1. Sorry, delta H1 plus delta H2 to the power of 1/2 square root 2G. This is what happens with upstream water 2 in the environmental flow spillway. This is what happens. So the moral of the story is that when you get to this elevation, to the elevation of the main spillway, through the environmental flow spillway, you have more than the environmental flow. This is not a problem from an environmental point of view. I mean, if you have more environmental flow, for the environment is not a problem. It may be a problem for the fishes if they want to climb up the fish ramp, and it's also a problem for your client that would like that the environmental flow is not exceeded. This is another story. But I mean, if you have no regulation, this is what happens. It's not a problem from an environmental point of view. It may be a problem for the fish ramp. It may be a problem for your client because he may say, okay, let me use that water. Let's not to release the water downstream, but let's use it. But what it means to me, what is important to me is that you understood the functioning. And it is basically very simple, but I know that it's not so easy to understand. Also in the classroom, it's not easy. Any question?
Yeah, I just want to make sure that I got it right.
Okay, please. Try to make
So
a summary.
Yeah, so when we have the water level upstream water 2, we have QD going through the diversion spillway,
Yeah.
and at the same time a higher flow than QDMB through the environmental spillway.
Perfect. This is perfect.
Okay. Okay.
Okay. And precisely through the environmental flow spillway, you have QE. Okay. Which is this one. Just give me. It is this one. Okay. And as I said, it's not a problem for the environment. It's a bit of a problem for the other reasons that I mentioned. So this is why some people say, I want to find a solution for this. And so they say the solution is to decrease L for increasing upstream water level. Because if you want to bring QE, this one, to the level of QDMV, this one, then, and you cannot, of course, have any influence on the elevation of water, delta H1 and delta H2, and you cannot have any influence on me because it's a coefficient, which is a behavior of the spillway. You cannot have an efficiency, you cannot intervene on gravity, you can only intervene on L. So some people, some clients say, why don't we put a gate there in order to restrict the width on the environmental flow spillway for increasing water level upstream? But sometimes the responsible authorities, they say no, because they don't want any gate on the environmental flow spillway. Is it clear, my final consideration?
Yes.
Okay, very good. And so I think we can stop here for today. And I put the video online, so I'm not saving the image of the blackboard because it's still too rough. I mean, I need to learn better how to write on it. But in any case, you will have the video, and the video, I think it's clearer because it shows you how the drawing on the screen evolved. Okay, so if you don't have any other question, let's meet on Monday, same time, and we will have the presentation. Okay? Very good. Thanks to you all, students. It's for your patience. I will improve. Bye bye. Ciao.